let's get started. I want to welcome everybody to this rapid interactive session. It's FrA02, and we have a great collection of talks. Kind of the focused session is on learning. And before I get started introducing our keynote speaker, I want to just say a few reminders. First of all, we have an award ceremony this afternoon at noon, so I encourage you to come to that. And we're going to be selecting the rapid interactive sessions. Basically, you've got a little voting system set up for you to get the People's Choice Award for the different presentations. So for this session, I'll send out a Zoom link shortly in the chat for everybody, and I'll try to remind you throughout the talk. And then there's the Hugo Schuck Award, which I'll send out a link for that as well. So for you to take a look at and also vote. And then I do want to remind everybody, we have a closing reception, okay, a virtual closing reception at 6:15. So the time is actually 6:15, not 7:30. That's in the schedule. So please stop by. You'll have to bring your own drinks, unfortunately. But we plan to have, just to get everybody together, and we've got a little video collage of virtual ACC that we'll show. And I hope everybody's having a good time. So let me go ahead and get started and just tell you a little bit about kind of the format here. We're going to start first off with our keynote talk, which is about 12 to 15 minutes or so, and then we'll have a 5-minute Q&A. And after that, we'll move into the 3-minute talks that are going to be played back to back. So there's no Q&A during that session. That'll last roughly a little bit over an hour. And I want to remind you, after this, this webinar session, you want to turn your attention to going to the interactive portion, and that is each author of these papers here will have a Zoom link on the schedule on the online program. You will visit them and interact with them further. So from 11 to 11:45 a.m. The authors will, probably show more slides and more videos, and you can actually interact and ask questions directly. Okay, it is my great pleasure to introduce our keynote speaker, Sandra Hershey. Sorry if I mispronounced the last name, from the Technical University of Munich. And so she's going to give us our keynote titled Anticipating the Long-Term Effect of Online Learning in Control. And I'm going to go ahead and just play her video, and then and I want to remind the audience that we do have a Q&A feature here in this webinar, or this for her presentation. So feel free to type your questions in, and she will answer them the same way by typing back, and then we'll have a live Q&A afterwards. Okay, thank you, and let's welcome Sandra.
Hi everyone, my name is Sandra Hirche, and it is my pleasure to present our work as keynote for the Rapid Interactive session here at ACC 2020. This talk is about online learning for control and how the anticipation of learning may improve control performance in the long term. This research has been performed mainly by PhD candidate Alexandre Capone and myself. Whenever systems are highly uncertain, learning control is a promising approach. Our research in this area is motivated by human-machine interaction, as for example robotic rehabilitation as illustrated on the left, and closed-loop deep brain stimulation as illustrated on the right. These systems comprise highly complex but unknown dynamics, which are difficult to model from first-order principles. Furthermore, in human-centric and many other applications, offline learning is not an option. So the question is, how to design controllers that learn online in order to improve the control performance. Learning control is a rich and rapidly growing field which has seen a reconnaissance due to the advances in machine learning. In this talk, we are concerned with the setting illustrated here on the right. The system is largely uncertain as indicated by the gray shaded area. The little available knowledge is represented by the white areas with the blue crosses. The objective for the control is to drive the system from the initial state x0 to the goal state. Obviously, control must navigate them through an uncertain space. There are essentially three control paradigms to address this problem. The so-called offline methods design the controller with a priori collected data. This is the most standard technique where system identification and control is separately executed. But also some reinforcement learning approaches fall into this category. Yet, if the model uncertainty is too high, control may easily fail. The second category spans all approaches where the controller is updated online during operation. Most classical adaptive control approaches fall into this category. Yet the learning there happens in a passive fashion, while the controller merely tries to reach the control objective and exploration happens only accidentally. As a result, the closed loop has a potentially poor performance. The controller in a third category attempts to simultaneously explore and exploit, such that the overall goal is reached robustly with high performance. This is also known as dual control. The idea of dual control has been around for quite some time by now. However, in the light of advanced learning techniques, in particular with non-parametric models, there arise new challenges, which we will consider in this talk. Let's have a look at the problem in a more formal way. We consider nonlinear dynamics with unknown part G. In this talk, we assume that G is represented by a non-parametric model, a Gaussian process, in short, GP. We consider an online learning control law where the data is collected to learn about the unknown G and thereby improve the control. As an example, G is directly learned in a model-based control law. The objective is to design a theta parameterized feedback policy which minimizes the expected finite horizon cost. Here, the expectation is taken with respect to all possible realizations of the unknown function G, which is represented by a probabilistic model, our GP. Solving this stochastic problem is computationally prohibitive. In order to reduce computational complexity, in this talk we present a sampling-based approximation technique, which is called sample average approximation. We combine it with Gaussian process dynamical models and show that the approximate solution converges to the true solution of the optimization problem. To this end, we will also need to predict the system behavior over multiple time steps. And we will see that the multi-step prediction for GP dynamical models is non-trivial. Let us first look at the uncertainty description via a Gaussian process. GPs belong to the class of probabilistic non-parametric models. A GP is a collection of random variables of which any finite subset is jointly normally distributed. On the left-hand side, you see a GP regression based on three training data pairs. The blue line describes the mean function. The shadowed area describes the standard deviation of the prediction for a test input. You can observe that it increases with distance to training data. In fact, a GP represents a distribution over functions, and on the right-hand side you see possible function samples, which are all compatible with the GP description on the left. GPs have become quite popular as they have a rich function space, and they naturally quantify epistemic model uncertainty. One of the main limitations is scalability with respect to the number of training data points. There are some promising advances towards real-time regression, but still GPs are clearly better suited for sparse data regimes. In our problem setting, we assume that the unknown function G is drawn from a GP. In contrast to classical regression, this constitutes a Gaussian process dynamical model now, as the GP maps from one to the next step of the state. Now consider we would like to predict the state evolution starting from this normally distributed x0. The probability distribution of x1 depends on x0 as expected. But x1 is now the input to the GP and the output x2 depends on both x0 and x1. In fact, the probability distribution at time t depends on all previous states, hence results in a non-Markovian dynamics. This makes it non-trivial for analysis and also computation. For the multi-step prediction in this work, we employ an equivalent formulation of the GP dynamical model, which makes it compatible with the later application of the sampling-based optimization algorithm. Here we leverage the fact that the conditional distribution on the previous data is still Gaussian. The dynamics is driven by an IID noise sequence theta, And the mu and the sigma here represent the mean and variance, which depend non-linearly on a whole state sequence up to the point t. Hence, here we employ the ideal version of the multi-step prediction. Using the whole history of data for the prediction for the next step is possible only for limited time horizons. So for the sake of completeness, we would like to point out that there are various approximation techniques to reduce the computational demands of the multi-step prediction. Here on the left, you see an example of finite memory prediction, where the prediction is conditioned only on the most recent states. In our recent work, we are able to prove probably bounded estimation errors for this type of approximation. Another popular technique is moment matching, which attempts to fit a Gaussian distribution to the distribution of the current state. We come back now to our original problem, design of the optimal controller via the stochastic program. We will see that our controller will have dual features. The first key ingredient here is the online learning aspect. The controller does not only depend on the parameter theta, but also on the whole history of data. As an example, consider a feedback linearization control where the system model is continuously improved online via learning. The theta then represents the feedback gain. The second key ingredient is the optimization over a time horizon larger than 1. Considering the online learning law in this stochastic optimal control problem incentivizes active learning, as long as it pays off in the long term by improving the control performance later on. So it makes the controller aware of the influence of its current actions on future observations. Hence, the learning is anticipated. The resulting control will have dual features. The exploration and exploitation trade-off is implicitly determined by the level of uncertainty in the model and the cost function. In order to compute the optimal control parameters, you would ideally like to compute this expected cost over all possible realizations of the GP model. This means that we have to compute this integral over multiple steps, but this is in general intractable. Therefore, we employ here a sampling-based approximation called sample average approximation. The idea is to draw a finite number of samples from the problem's probability distribution to substitute the integrand by a summation over the sampled scenarios. Here the idea behind sample average approximation is illustrated. We see 3 different trajectories sampled from the same prior distribution to obtain the approximation of the expected cost. So capital M would be 3 here. The optimization problem for the approximated cost is then deterministic and can be solved with the appropriate solver. Also note that the individual sample passes can be computed in parallel, while the optimization iteration is centralized. By exploiting now the properties of the GP, we are able to show that sample average approximation converges to the true optimum. The key features to prove this are the IID sample-based representation of the multi-step prediction for the GP dynamical model and the continuous differentiability of most interesting kernels. The result is an algorithm that provides a solution which converges to the true solution with probability 1 as the number of sampled scenarios increases. Here we see an illustration of how the approximate cost function converges with growing number of samples from the left to the right. In blue, we see the true cost function depending on the parameter theta. In red, it's the approximated cost. With only a few scenarios, here on the left, there's quite some difference between the true and the approximated cost. Yet the approximation error goes to 0, with m going to infinity. Now we look at the simulation example for illustrating the behavior of the control law. In particular, we will compare the performance between a controller with anticipating the online learning and a controller that disregards the online learning. We consider this nonlinear dynamics and this unknown function g. A Gaussian process with a squared exponential kernel was trained a priori with a small set of 100 training data pairs. In the picture here, you see the ground truth of the function g in red. The training data are depicted as black crosses, and the blue line represents the mean function, and the blue shaded area shows the standard deviation of the Gaussian process. We consider a tracking problem where the tracking error shall be minimized over 150 time steps. The controller is composed of a feed-forward term based on the Gaussian process mean and a feedback term parameterized by θ1 and θ2. The sample average approximation is applied here with 200 scenarios. Here on the left, we see the predicted optimal behavior if learning is not anticipated. In this case, the optimizer does not take any learning-induced control law updates into account. Shaded in gray is the area where prior training data is available. The state is depicted in blue, in red is the desired trajectory. As we can see, the control law barely attempts to track the desired trajectory, and the running costs that are shown at the bottom here in blue remain high. This is because learning is not anticipated. The uncertain region of the state space is expected to remain uncertain, and venturing into that region would only yield highly unpredictable behavior. Here the control is conservative in the sense that it avoids uncertainty, and it results in a rather poor performance. By contrast, if learning is anticipated, the controller attempts to track the desired trajectory, even though it means leaving the known region of the state space. This is because it knows that the model will improve eventually, and so will the control. There is a learning transient with high running costs in the beginning, where the controller explores. But already after 40 steps, the learning is complete. The controller starts to exploit, and the running costs become significantly lower. As a result, the total control performance is significantly improved. Now I would like to conclude the talk. We have considered the problem of active online learning control here with Gaussian processes. We demonstrated the issue related to multi-step predictions for GP dynamical models, which result in a non-Markovian dynamics. In order to address the computational complexity problem of the involved stochastic optimal control problem, we have considered a sample average approximation and show that it leads to an arbitrarily exact approximation of the optimal solution. Finally, as expected, the resulting controller enjoys dual features, implying that there's a learning-induced transient, but also an optimal trade-off between exploration and exploitation. Clearly, this is only a first step, and there are many open problems still, in particular in the challenging area of learning control with guarantees. Our current work concretely related to this problem concerns sample complexity guarantees and its application in receding horizon fashion. The issue of learning control with guarantees is also a larger topic at our chair, currently in conjunction with application in rehabilitation and underwater robotics. Apart from Alex, I would also like to particularly thank Jonas Umlauft, Thomas Beckers, and Armin Lederer for all their contributions in this exciting research area. Finally, I would like to mention that in addition to this work, we also have another contribution presented here in the Rapid Interactive session by Armin on confidence regions for simulation with learned probabilistic models. And with this, I would like to stop. I would like to thank you for your attention, and I look forward to an interesting Q&A session.
Great, thank you. Let me go ahead and stop screen sharing here. And yeah, so we're going to open up the floor for questions. So Sandra's going to answer them. Go ahead, Sandra. Go ahead, Sandra. You can.
I should, yeah, first of all, thank you very much for inviting me to this keynote. We had one question already in the chat window that I answered. So the question was, can the function f of x and u be also 0 in this model? And I said yes. So basically you could put all prior knowledge about your system into this function f and put all uncertainties into the function g.
So there's some more open questions that are the.
I didn't see that there are more open questions. I'm sorry.
Like a great number of them actually too, 4 more.
Okay, so I'm sorry, I should have answered it. So there's a question, is there measurement at every time step? Does there have to be? So of course, at the moment, first of all, we consider state feedback and we assume that there will be a measurement at every time step, but it's an interesting question. I haven't, to be honest, I haven't thought about that. Essentially, well, okay, I don't want to answer this question in detail now, but I think it's an interesting problem to ask whether you have to have a measurement at every time step. For closing the feedback loop, yes. For the learning part, I don't think so, because you could also approximate your model through sparse GPs, but then we would have to leave, so then the approximation error becomes relevant, and so maybe you cannot anymore say something about the convergence, or you become epsilon optimal. Okay, then there's another question. Why does the IID assumption hold for the state samples? So we use an equivalent formulation where you can basically represent the sequential prediction, or the sequential drawing from a GP by sampling from an IID noise, and the IID assumption holds basically. So the conditional probability distribution conditioned on all previous data is still Gaussian because it's a Gaussian process. But, and this is what you see, but the mean and the variance they're dependent on all the previous data on the past history. So they become quite complex. And so this is why it's a bit hidden, but it makes it applicable, or it makes sample average approximation applicable. Do we have a forgetting factor to keep the learning computationally feasible? Also, do you update the hyperparameters? So at the moment, we don't have a forgetting factor, but that's definitely something you would need to consider if you learn over longer periods of time, in particular when you use a Gaussian process, because Gaussian processes are known to be limited with respect to scalability in terms of the size of data. So it's with n exponent 3, yeah, that scales. So it does definitely, in a practical application, it would make sense to smartly forget. So there's a question on how you smartly forget. One way is just to consider last window of data. We have done that in another publication, and we can even give some estimation error bounds for this type of window GP or window based prediction, where I'd only consider last n steps. Do we update the hyperparameters? No. So we consider that we have initially a training data set, a very limited training data set, where we train on our GP on, but we do not intermediately update the hyperparameters. Okay, then there's one more question. Clearly you need enough time to learn. Can you predict the prior and expected time of learning to ensure that the early penalty is worth it? Well, that's again an interesting question and very difficult to answer. Okay, it's of course that the learning transient that you see is dependent on the uncertainty in your model and on the cost function. So how well, I would have, it's a very interesting question, but to be honest, at the moment we cannot predict this expected time of learning. What you could do if you, for example, think about safety, then into the cost function you could put soft constraints. So in terms of a penalty, which would at least prevent to enter dangerous areas, not with guarantees, but in a probabilistic sense. Okay, so these were most of the questions that I have, that I've seen now.
There was a question in the chat about.
Oh, there are more questions.
The dimensionality of the.
I see more questions. Okay. What happens if the assumed dimension of the state space is not the same as the actual dimension of the system? Okay, of course, that's always a question. Basically, you put the, and then it becomes tricky. So if your state dimension of your assumed state dimension is lower, then you basically, all the uncertainty coming, or the variability coming from the, let's say, this projection on this lower dimensional state space would somehow be mapped on some, probably the Gaussian process would interpret it as noise, as a process noise, and then it becomes tricky. So of course, then no longer any guarantees can be given, and yeah, so probably Gaussian process would interpret it somehow as noise, or you would have to interpret it as noise. What kind of kernel do we use for the GP? So here in our, basically in the paper, we consider in the simulations a squared exponential kernel. In general, we have, we can consider any continuously differentiable kernel. So because this is one of the fundamental assumptions that you have to make. So for the sample average approximation, that you have continuous differentiability of the kernel, and that's basically the only limit. That's also the limit to which you can reliably predict. So you have to put the same assumption on the uncertain function g.
Okay, in the interest of time, we're going to move forward. In the interest of time, sorry, we're going to play the rest of the video. So what I encourage everyone to do is get on Slack if you want to ask more questions, or visit her during the interactive portion, which is coming next at 11 o'clock. All right, well, let's go ahead and thank Sandra for the wonderful keynote talk. And now I'm going to turn my attention to playing the other videos. So let's see, where is my video app? Sorry, here it is. Tell me if this is good. Are we good? All right, I'm gonna go ahead and play this. And again, just as a reminder, for those who've just come in, we will have now 3-minute talks back to back for the next hour or so. And then afterwards, the interactive session starts at 11. So all the speakers will go to their respective Zoom rooms and further present and interact with the attendees. And don't forget about voting for the People's Choice for the RI for this session, and also the Hugo Shuck Award, which the link will be put in the chat. Make sure you copy and paste that, because once we close this webinar, that chat history disappears.
Hello, my name is George Kontoudis, and in this video I will present your work on online model-free motion planning in dynamic environments. The motivation of this work regards realistic motion planning, which takes into account kinodynamic constraints. We also consider temporal constraints, as in dynamic environments we need to navigate at specific time frames, which leads to finite horizon formulation. System dynamics are often difficult to derive and may change throughout the navigation. But even if we have the dynamics, it is computationally expensive to compute the optimal control. And therefore, we cannot implement in real time the controller. We also consider communication security aspects by communicating as little as possible, leading to an intermittent control formulation. The main idea of this paper is shown here. We define the continuous time Q function as the optimal value function, the intermittent Hamiltonian, and the time trigger Hamiltonian. Next, by doing some mathematical manipulation, we get the augmented representation of the Q function. Then we use some elements of the augmented Q matrix to reconstruct the intermittent controller, which is a function of the sample state. We employ an intermittent condition to close the loop, which is based on an inequality of the squared norm error gap. The main theorem of this paper shows that the origin is globally asymptotically stable equilibrium point of the closed loop system under some inequality conditions. The proof is Lyapunov-based, and we consider both flow and jump dynamics. The steps that we follow are shown here. First, we compute the global path using the RTX, which can be used in dynamic environments. Next, we execute the intermittent model-free optimal control, and we measure the kinodynamic distance. The kinodynamic distance is the distance of the straight line connecting the waypoints to the actual location of the robot. Next, we augment the obstacles based on the maximum occurred kinodynamic distance, and we replan with RTX. Let's see how that works in practice. We can see the robot navigates. In white line, you see the global path. In red line, you see the traverse path. The obstacles are shown in blue, and they appear and disappear in an unpredictable fashion. In pink, you see the augmented obstacle space. On the right-hand side, you see the current kinodynamic distance, and on the left-hand side, you see the maximum kinodynamic distance, which we use to augment the obstacles. As you can see, the robot can navigate from a start state to a goal state using the intermittent optimal controller and RTX. Our method is completely model-free. It works in an intermittent fashion, it operates in real time, and it is even applicable in dynamic environments. Thank you.
Hi, my name is Chase Dowling. I'm a scientist at Pacific Northwest National Laboratory. This is some work I did wrapping up graduate school under my advisor, Baosun Zhang, where we applied the concept of transfer learning to HVAC system fault detection. Lots of new buildings have much smarter HVAC systems, and they're all streaming lots of performance data. This performance data can be used to improve HVAC system efficiency and maintenance with statistical and machine learning tools. The problem with deploying these tools is that it requires lots of ground truth data. And most buildings are much older than these new HVAC systems and lack lots of ground truth data. Transfer learning can address this shortcoming, where you learn a verifiable model on a building for which you have lots of data, then use a small amount of data from a target building to transfer the model, rather than learning a new one from scratch. Very briefly, what we do is we collect a bunch of data on building operations and learn a linear model with that data as input plus some Gaussian noise, where the linear model predicts the next time steps power consumption on various components of the HVAC system. In the paper, we use a polynomial basis. And the way we do fault detections, we say there's two probabilities of something occurring with that linear operator A. Either the system's operational and the probability that the observation that we see on HVAC system power consumption is true or is high given the true model and those inputs, or the observations that we see come from a model that isn't A. What we do to derive a classifier is we put a matrix normal prior on this faulty transition matrix A and derive an analytical expression to classify whether or not a sequence of observations is from either an operational matrix A or some other faulty matrix that we haven't seen before. To apply this concept of transfer learning, we simulate a building in Energy Plus, generate lots and lots of samples, and we transfer our model A to a real building, this medium-sized office building at the PNNL campus. And in the context of the model that we learn, we use weighted least squares. We can see the performance here, that for a model that you bootstrap with lots of learned data from a similar building, it takes far less consecutive samples to achieve a much more accurate model than a model learned from scratch. And subsequently, the performance of that transferred model is functional. If we simulate faults, then the sequence of observations detects a fault and detects normal operations with or without a fault. The usage of weighted least squares is purely contextual, given the model that we chose to use, a kernel regression. In the paper, we also learn a neural network just to show that you learn the model, neural network model, and then transfer it by initializing the weights and performing gradient descent on samples collected from the target building. So hopefully we've demonstrated that transfer learning is a good option for buildings for which we don't have lots of ground truth data.
Hello, my name is Hoàng Hải Nguyễn. I am a PhD student in Laboratory for System Theory and Control of Professor Rolf Vindersen in Otto von Guericke University, Magdeburg in Germany. I would like to present the work I have done with my colleagues and my professor under the title Towards Nominal Stability Certification of Deep Learning-Based Controller. When we try to integrate machine learning into control, one of the crucial questions is, how can we provide performance and safety guarantees for the learning supported systems? In this work, we look at the situation when we already have a baseline controller that can deliver a good closed-loop performance, and the nominal model of the plant can be obtained, but the mathematical description of the baseline controller may not exist. An example might be a human operating a car, where the dynamics of the car can be modeled sufficiently well, but a mathematical model of a human control actions is not available. Or it can happen when baseline controllers are only available in hardware as they have been designed a long time ago, or the existing baseline controller may be computationally expensive. In those scenarios, we want to learn the behavior of the baseline controller with a neural network, and the baseline controller doesn't need to provide any guarantees. So the question is, can we verify safety guarantees for nominal system with learning-based controller? To do this, we use specific type of deep neural network called non-autonomous input-output stable network, or in short, NICE-NET. And we provide an explicit formula for computation of the number of hidden layers of the neural network, which are formulated by using Lyapunov-based techniques. Briefly speaking, NICE-NET is a special type of residual network. Theoretically, when suitably trained with the tangent activation function, if the number of layers denoted as n approaches infinity, the NICE-NET becomes an affine mapping, and the output will converge to a specific point that depends on the input. However, in reality, we can't have infinite number of layers, and we also do not want to have infinite layers, because what we want to learn in general, a nonlinear function, not an affine one. The interesting thing is that the difference between the output from the finite layer NICE-NET and the convergence point is always bounded by a value that depends on the number of layers n. Then we can transform the real system into the imaginary auxiliary system with a disturbance that is bounded by a value that depends on n. Use Lyapunov techniques and the assumption that the auxiliary system can be stabilized by an affine controller. We can derive a sufficient condition to verify the stability of the closed-loop system based on the number of layer n. I hope our results sound interesting for you, and I am looking forward to having opportunity to discuss with you in the upcoming interactive session. Thank you.
A data-driven falsification-based model of human driver behavior. The field of human driver behavior modeling has been the subject of extensive research. For example, human drivers manifest as a disturbance to an autonomous vehicle seeking to follow a path or plan. In this context, an effective driver model has consequences for both the control synthesis and control evaluation problems. A reasonable question to ask is how such a model can be constructed. A simple model could rely upon only the physical limits of a disturbance vehicle. An upside to this model is its conservatism, that is to say, it subsumes all possible human driver actions. On the other hand, this conservatism is usually unrealistic. Human drivers rarely operate at the extreme limits of their vehicle's capabilities, and therefore such a model is uninformative. The simple model performs poorly because it does not leverage information about the driver's surroundings to describe her behavior. In the language of mathematics, a high level of uncertainty results in a large set of candidate human actions. We sought a more reasonable human driver model by incorporating environment information to our system state to reduce the driver action uncertainty. Translating this to a clear problem statement, we desire mapping from a finite history of the human driver and her environmental states to a set of actions. We decided to leverage observations of real drivers to construct such a mapping. Our set-valued mapping needed to be conservative, like the simple model, while still being informative. In order to find this set, we sought to create a boundary around real-world observations. Of course, many boundaries are possible, including the simple model we sought to improve. Our approach was to learn driving norms by using parametric signal temporal logic. This formalism allowed us to express common human behaviors as specifications. One example is stopping at red lights while still potentially creeping forward. If we could enumerate all driving norms, then our rules would serve as the aforementioned set boundary. However, listing all driving norms is not straightforward, and furthermore, the temporal logic representation of the set boundary may be difficult to use for different applications. Instead, we created a handful of specifications and sought counterexamples for only those specifications. We reasoned that because our rules are constructed from real drivers, violations of our specifications were potential examples of non-human actions. That is to say, they represented actions that human drivers would not take. By following this procedure, we had a dataset that was ripe for classification. The classifier led us to a description of the set of human driver actions given a finite history of the driver and her environmental states. Our approach enabled us to reduce the uncertainty of human driver actions in certain cases. However, we believe that there is potential for improvement to our methodology. The first would be a larger training dataset, which we hope to resolve in subsequent work. The second improvement would be to consider a larger class of smooth signals as a basis for STL falsification. By creating signals that appear to be more human-like, we may find more insightful classification results. And finally, we would like to quantify the uncertainty of our classifier. Work done in the space of sampled convex programs may offer some insight, but to our knowledge, these approaches have been applied to only stationary points as opposed to the time series we consider here. Thank you very much for your attention.
Hello, everybody. Welcome to our presentation today. Today, I'm going to present our work on automata-guided semi-decentralized multi-agent reinforced learning. This is a joint work with Dr. Xiao Li and Dr. Kelly Belta. So the problem we're going to solve is to deploy a multi-robot team to satisfy a tactically co-safe truncated linear temporal logic task specification by a multi-agent reinforced learning technique. And there are challenges to solve this problem. First is the task assignment among the heterogeneous agents. And the second is we need a quantity to track the satisfaction of SCTL-TL and coordinate the agent to learn cooperatively. And the third, we want to do this in a non-centralized way, because centralized learning methods are intensive in terms of memory and computing time. So here comes our method. We want to design a temporal logic reward, which is a quantity metric called the robustness degree to measure how a SCTL-TL formula is satisfied. Then through this continuous quantity, we transform the satisfaction of a SCTL-TL from Boolean to continuous. Then we augmented the Markov design process by our automata states. Then this means that we will have the automata states as a part of the MDP states to check how far we have gone to satisfy the temporal logic formula. Then through this as a continuous reward, we transform the Boolean satisfaction of the temporal logic to a continuous one. But this is still centralized, and we want to make it semi-decentralized. So we use the automata state again. The automata state Q here is shared among all of the agents to tell all of the agents how far the team has gone to satisfy the temporal logic formula. Then through this coordinator, the task assignment could be learned, and each agent can learn in a decentralized way using this decentralized reward. Then we test our algorithm in a grid world task, and the formula to satisfy is this, eventually A, B, and C. So we compare our algorithm to the centralized learning. It turns out that the performance or accumulated reward of our semi-centralized algorithm is almost exact to the decentralized one, but the number of the episodes required to converge is much smaller. Which justifies the advantage of our semi-decentralized algorithm. So this is all I have for today. And
Hi everyone, I will be presenting our work on extended dynamic mode decomposition with learned Kubernetes functions for prediction and control. This is joint work with Daniel Pastor and our other co-authors. Today, there are many autonomous robotic systems in development for both commercial and scientific applications. Examples include autonomous driving, drone delivery, planetary exploration, and mobility recovery for paraplegic patients. And they all operate in complex environments while performing a wide range of tasks. And this motivates combining machine learning and control theory to enable the design of high-performance controllers with safety and performance guarantees. One way to approach learning and control for dynamical systems is through Koopman spectral theory. And the Koopman theory describes nonlinear dynamics as flows of observables that are functions of the state space that lift the state variables to a space where they are linear. And the extended dynamic mode decomposition has been presented as an efficient numerical algorithm to find finite dimensional approximations of the Koopman operator. And for control systems, this results in a lifted linear state-based model that readily lends itself to well-developed linear control design techniques, such as model predictive control. A key challenge in ED&D type learning, however, is how to choose these nonlinear transformations. And in this work, we're proposed to use Koopman eigenfunctions, which are defined similarly to eigenvectors for matrices. And the eigenfunctions are attractive because they describe key characteristics of the system, and they are guaranteed to evolve linearly in time. So our method can be summarized as follows. First, we assume that we have some unknown dynamics, but that we have a nominal linear model and a stabilizing controller that can be used to collect data. Then our key contribution is a method to learn Copenhagen functions, and this is done by constructing eigenfunctions for the nominal dynamics, then to learn a diffeomorphism from data, and this diffeomorphism is guaranteed to exist under certain conditions. And then based on that, eigenfunctions for the unknown nonlinear dynamics can be constructed. Then we use these eigenfunctions as lifting functions in a ED&D type learning method. And finally, we do control design with model predictive control, which can be formulated as a efficient quadratic program, taking state and actuation constraints into account and can utilize the full nonlinear dynamics as encoded by the learned dynamics. Then we do initial demonstrations of our framework on a simulated carpole example. And both in open loop prediction and in closed loop control, we significantly outperform both the nominal model and classical ED&D. And for trajectory tracking in a closed loop task with MPC, we reduce the total MPC cost with 97% compared to the nominal model, and with almost 90% compared to the ED&D model, resulting in both lower tracking error and less control effort to be needed. Finally, based on this, we conclude that Copenhagen functions is an attractive way of significantly improving both tracking and closed loop performance of ED&D type learning. And for more details, please see our full paper and our publicly available code. And please also reach out if there is anything you would like to discuss. Thank you.
Hi everyone, I am Shayok, and today I will talk on robust reinforcement learning control for singularly perturbed systems. RL control can compute feedback gains without explicit system dynamics. However, with increase in dimensionality, full dimensional learning will require large learning time and result in dense structure. One solution would be to exploit the system structure. We consider singularly perturbed dynamics capturing timescale separation and design reduced dimensional control using only slow dynamics. Network system with clustering falls under this category, where we can first take a projection in a low dimensional scale, state space, and then learn the control in this low dimensional state space. And once the control has been learned, we can project it back in the original dimensional state space. In this paper, we have considered dynamic uncertainty coupled with this kind of SP system, represented by this state space equation, where Y represents the slow state, Z are the fast states, and rho dot dynamics are the uncertainty, which we assume to satisfy an ISS condition. Then the problem would be to solve this linear quadratic objective in a model-free setting using only the feedback of the slow state variables. The problem can be solved in this way by putting epsilon equal to 0, which helps us to move into a slow state space, which is represented by this idealistic variable ys. And if we want to solve an LQR problem in this slow state space in a lower dimensional scale, then we will require to solve this trajectory relationship, which is in terms of ys. However, as epsilon is not exactly equal to 0 in reality, we need to replace ys by the actual variable yt, which can be done in this algorithm, which basically consisting of two steps. The first step is to gather sufficient amount of data in terms of y, u, and d, and then solve this least square equation, which basically tries to solve this equation, this trajectory equation, in terms of y. We also provided theoretical guarantees where we start with the suboptimality result, which says that the solution of our algorithm is O epsilon perturbed from the ideal solutions. Then we looked into the stability with bounded disturbance, which states that the closed loop will be ISS with sufficiently large Q. We considered this assumption as denoted by assumption 3 on the Lyapunov function of the uncertainty to provide stability of slow subsystem. Then to characterize the interconnection, we first relax this assumption, which leads to a nonlinear small gain theorem. However, using assumption 3 can help to give us a strong stability guaranteed using the results of asymptotic stability of the slow subsystem. We conclude this talk with the simulation of cluster network with 9 layers. The dynamics is given by a Laplacian with 2 slow eigenvalues because of the presence of 3 clusters. It turns out that full dimensional learning with exploration will require around 4 seconds of time to gather data, whereas if we use the projective design, it will only require 1 second of data, and it will improve the damping of the slow eigenvalues with better performance. And the advantage of our algorithm will be more if the number of agents are much higher than the number of clusters. In conclusion, we combine the ISS-type dynamic uncertainties and the SP theory in the RL framework to perform fast learning with theoretical guarantees. Thank you.
Hi, welcome to my talk on ZapQ learning for optimal stopping. My name is Suhan Chen. This is a joint work with Adicia, Anna, and Sean. The goal in optimal stopping is, for a discrete time Markov chain, we seek to find the optimal stopping time tau star that minimizes this expected discounted cost, where gamma is the discount factor between 0 and 1, c is the per stage cost function, and the c subscript s is the terminal cost function. We define for each state the optimal value function as the minimum expected cost if the Markov chain starts at state X. We define the optimal Q function as the minimum expected cost when we choose to proceed at state X. The optimal Q function then induces an optimal stopping rule, which tells us to stop when the terminal cost is less than or equal to the optimal Q function. The goal in dynamic programming is to find the optimal Q function by solving this Bellman equation. In Q-learning, where the Q function is parameterized by a linear function, where theta is a parameter, psi is the basis functions, our goal is to find an approximate solution to the Bellman equation by Galerkin relaxation. More specifically, we try to find the theta star that solves this root finding problem. The F bar is defined as the expectation of the temporal difference function multiplied by the basis function. We then apply ZapQ-learning to solve this root finding problem. ZapQ-learning is the 2-time scale stochastic approximation algorithms. We prove that under very general conditions, the parameter sequence theta n obtained by ZapQ-learning converges to theta star almost surely. And the asymptotic covariance, defined by this way, which is often used to study the convergence rate of stochastic algorithms, is also optimal for ZapQ-learning under additional tightness conditions. We then study ZapQ-learning on a standard optimal stopping time problem. The first plot shows the average rewards connected by ZapQ-learning and the Kalman gain algorithm under different setups. You can see it here, ZapQ-learning clearly has better average rewards. In the second plot, we show the histogram of scaled errors for ZapQ-learning and the Kalman gain algorithms. We can clearly see that the empirical distribution of those scaled errors closely match the theoretical prediction provided by the central limit theorem. Thank you.
Good morning. I am Mukul Kagrani, and today I'll be talking about regret analysis for learning in a multi-agent LQ control problem. This is a joint work with Syed Mohammad Asghari and Ashutosh Nair at University of Southern California. So we consider a 3-agent system where each agent has a local state and takes an action at each time. Each agent has linear dynamics, and the agents are dynamically coupled. In particular, agent 1 affects the dynamics of agent 2 and agent 3. At each time, system incurs a quadratic cost, so the agents are coupled through both the cost and the actions. Each agent observes its own local state and also gets an observation of state of agent 1 at each time. There's a model uncertainty where the dynamics of agent 1, which we are going to refer by theta, is unknown to all the agents. However, we assume that the dynamics of agent 2 and agent 3 are known to the agents. So we use the notion of regret to quantify the performance of a policy. Regret of a policy pi over a time horizon of capital T is the expected difference between the cost accumulated under the policy compared against the optimal infinite horizon cost when theta is known to the agents. So our objective is to find a decentralized policy, which minimizes the regret. So this is an instance of decentralized team learning problem, since agent 2 and 3 also need to estimate theta due to the coupling in cost and dynamics. So we propose a Thompson sampling based decentralized learning algorithm. Thompson sampling is a Bayesian approach where each agent starts with a prior distribution over theta and then maintains a posterior over theta on the basis of its local information at time t. Then at some carefully chosen times based on a sampling condition, each agent generates a sample from its own posterior and then computes its action based on the optimal decentralized solution for its current sample. So the main theoretical result which we show is that the regret of the decentralized Thompson sampling algorithm is upper bounded by big O of square root t, where this tilde is hiding some logarithmic factors in time. So note that this is a non-asymptotic finite time bound on the regret of our algorithm. So this figure shows the regret of our algorithm as a function of time. And we see in the numerical simulations that the regret of our algorithm grows with the rate of square root t, which validates our theoretical result. So before I conclude, I would like to mention that the results of our paper can be easily generalized for any arbitrary number of agents under similar assumptions on the network topology. And with that, thank you for listening to our talk, and we look forward to seeing you in the upcoming interactive session.
Hi, I'm Natalie Burnett. I'm a PhD student at Caltech in John Doyle's group. And in this 3-minute talk, I'm going to tell you about the title of our paper. Throughout a season of Formula One car racing, 2 competitions are simultaneously being held. One is the Drivers' Championship, where drivers win points by winning races, and the other competition is for the engineers, who are recognized for the victories won in the cars that they designed. As my poster title suggests, the work that I'm presenting in a little while is not actually about Formula One racing, but about the relationship between reinforcement learning and robust control. In this learning session of ACC, I don't think I need to convince anyone that machine learning is an exciting research area. Suffice it to say that learning-based methods have been dramatically successful in a wide variety of problem settings. Now many are interested in reinforcement learning as a promising model-free data-driven control strategy, which has had encouraging results in simulation and even in some lab settings. So where does control theory stand in relation to these data-driven control methods? Through the work in our paper, we give evidence that the tools and methods of robust control theory are not becoming obsolete in the wake of model-free reinforcement learning, but rather fill an essential and complementary role. Much like a Formula One driver during a race, learning methods fundamentally optimize task performance above all else. Drivers do consider the safety of their driving style, but mainly to the extent that those concerns affect their performance. We argue that robust control and more generally model-based methods can and should fill the role of the Formula One engineer, whose job is not just to design fast, high-performance cars, but to ensure the safety of the driver and car by monitoring, diagnosing, and ultimately just preventing car failures. Both of these roles are essential, but the jobs themselves are very different and require very different approaches. So in the poster session, I'll tell you about the kinds of questions that arose in a simple toy problem when studying data-driven control from the engineer's perspective instead of the driver's.
Hello everyone, my name is Abid. I'm a PhD candidate at UC Riverside. My talk is about accuracy prevents robustness in perception-based control. Machine learning never fails to amaze us with its state-of-the-art performance, especially in control applications. However, when deployed in the wild, it miserably fails. The reason could be due to the change in the environmental conditions, perhaps by an adversary or nature. One of the important questions researchers are trying to answer is how to design data-driven algorithms that are provably optimal in the sense of performance and robustness. In this work, we show that robustness is at odds with performance, where optimizing one comes at the cost of the other. In particular, we focus on closed-loop settings with perception in the loop, where we want to control a vehicle equipped with a camera. The camera images are used to reconstruct the partial state of the system by feeding them into a trained perception map, which will give me a prediction of the vehicle's position with an error which we will call perception error. That depends on the training of the perception map and what dataset is used. To reconstruct the whole state, we feed the predicted position to an estimator, which we design based on our knowledge on the perception error. Then we feed the estimated states into a controller, which will give me a stabilizing input. And this input will depend on the estimator's accuracy, which depends on how accurate our knowledge on the perception error statistics. For instance, if my perception map is trained on nominal data and the system is deployed in nominal environment where the error statistics are known, I can design an accurate estimator. However, if I deployed my designed estimator in non-nominal conditions, it will diverge, as seen on the plot on the right. In this presentation, I will focus on how to design a linear estimator with gain k that operates well in different environmental conditions. In order to do that, we need to define metrics to measure how good the estimator is. The first metric is accuracy, which is the estimation error. The second metric is sensitivity, which measures how accuracy changes with respect to the perception error. Note that a lower value of each of these metrics is desired. To design an optimal estimator with respect to these metrics, we cast this optimization problem, where we minimize sensitivity of our k subject to a constraint on the estimation error. The solution of the optimization problem gives me a gain k star with minimum sensitivity and estimation error delta, and solving this over a range of delta, we get this trade-off curve between sensitivity and accuracy, where each gain for a specific delta corresponds to a point on this curve. And this result tells us that minimizing sensitivity comes at the expenses of accuracy. To validate our results, we consider this closed-loop system where we want to track a desired trajectory. We simulate our system in two different environmental conditions, clear weather on the left, rainy weather on the right. We then design two filters, a Kalman filter and a robust filter. And indeed, this validates our theoretical results where we observe that the Kalman-based system performs better in nominal conditions and the robust filter-based system performs better in non-nominal conditions. Thank you for listening. I look forward to discuss this paper with you in the interactive session.
Hello, my name is Armin Lederer and I'm going to briefly present our paper entitled Confidence Regions for Simulations with Learned Probabilistic Models, co-authored by King Hao and Sandra Hirke. In recent years, probabilistic models obtained from machine learning have been increasingly used in simulation-based control approaches. For example, applying ensembles of probabilistic neural networks in model-based reinforcement learning has led to state-of-the-art sample efficiency. And Gaussian processes allow to capture the uncertainty of the environment for model predictive control. In all of these approaches, we can observe that the propagation of the uncertainty in forward simulations is crucial for control. However, due to the complexity of the models obtained from supervised machine learning, we typically cannot calculate the uncertainty propagation analytically. In our work, we have considered a special case of this problem. For this, we consider noisy dynamical systems with deterministic but unknown dynamics f and observation function h. Both functions are perturbed by noise, such that the system generates random trajectories. We assume that a model of the system is available in the form of a random process, for example as obtained by Gaussian process regression or Bayesian neural networks. Using this model, we can generate random trajectories as well. Since we deal with a random model, we often want to define confidence regions for the states and outputs. Assuming that we have a well-calibrated model, the question is what is the probability delta that a trajectory of the real system does not stay inside the confidence region. We approach this problem using Monte Carlo sampling. Depending on the structure of the model, we either sample the model parameters and then simulate the system, or we iteratively construct sample trajectories by sampling the next state and conditioning the model on it. Using Hofding's inequality, it is straightforward to show that delta can be bounded by the depicted expression, which depends on the empirical probability computed based on the sample trajectories, the number of samples, and a parameter t. Now the question is how we should choose the number of sample trajectories and the parameter t. If we choose the confidence regions large enough such that we can expect all sample trajectories to lie in them, we show that the depicted bound for n guarantees that a desired confidence level is achieved. Then we show that the optimal value of the parameter t can be obtained by solving a convex optimization problem. We apply our theoretical results to an inverted pendulum system with noisy observations. As a probabilistic model, we train a Gaussian process and define the confidence region based on 100 sample trajectories of it, which results in the hatched area. Using our theoretical results, we determine the number of samples and the value of t to guarantee a value of delta equal to 0.05 for this confidence region. In comparison to a Lipschitz-based approach for uncertainty propagation, which is illustrated by the red shaded area, the trajectory sampling provides far less conservative confidence regions. I look forward to the opportunity to discuss this paper further with you. Thank you very much.
Hello everyone, I'm Yuan Lin. Today I'm going to introduce our paper toward resilient multi-agent actor-critic algorithms for distributed reinforcement learning. It is known to all that the reinforcement learning has achieved tremendous success in all kinds of areas, like robotics, game of Go, autonomous driving, and data game. In order to apply it to the large-scale networks, including the social platforms and the online economy networks, people propose the multi-agent reinforcement learning. Under this problem, the agents could collaborate, compete, or both with each other to reach some goals. But all of these require all agents share the correct information to their neighbors. However, in some real problems, there exist some bad agents who will share the incorrect information to their neighbors. We call these agents as Byzantine adversary or Byzantine agents. Consider a system if each worker agent shares omega I to the master agent. After doing the average, the master agent shares the omega 0 back to each worker agent. Then all worker agents get the average value of the initial worker agent's values. If there exists a Byzantine agent, agent 2, who will share the incorrect information omega 2 theta to the master agent. If the difference between omega 2 and omega 2 theta is very large, then the value received by all worker agents would be totally different from the correct one. From this example, we know that the Byzantine agents could cause a huge error on the result. To reduce the effect of the Byzantine agents, we use trimmed mean method. We assume that there are at most F Byzantine agents in this system. If the omega I we mentioned before is a scalar, then we can find an agent set U obtained by removing the agent whose value belongs to the largest F or smallest F element. Then we can change the update of master agents to average the values of agents from the agent set U. As for the high dimension omega I, we can apply trimmed mean to each dimension's update. By using the trimmed mean method, it can not only reduce the effect of the Byzantine agents, but also get a result which is a convex combination of the non-faulty agents' value. Back to our paper, this is the outline of our paper. We not only propose the trimmed mean-based actor-critic algorithm to deal with the Byzantine problem, but also propose a communication-efficient algorithm to reduce the communication cost. You can check the detail of the method, these algorithms, and the result in our paper. That's all. Thank you.
Hello, my name is Kaliang Tan, and I'll be presenting my paper about robustifying reinforcement learning agents via action-space adversarial training. The adoption of cyber-physical systems are becoming more and more prevalent in some sectors such as manufacturing, transportation, energy, and so on. As we embrace the advancement in machine learning and deep learning to aid in these sectors, we must also be aware that these technologies that improve our livelihood can also cause irreparable damage if attacked by malicious attackers. Researchers in the deep reinforcement learning community has made significant advancement in recent years, which demonstrated the capabilities of deep RL in data-driven systems and control applications. There has also been numerous studies done to perturb deep RL agents in the state space and robustify them against it. However, there has been relatively less studies to robustify deep RL agents against action space actuated attacks. In this work, we show that a deep RL agent that was initially susceptible to action space perturbation can be robustified against similar perturbations through action space adversarial training. The generic interaction between agent and environment are as shown here. The environment outputs a state and reward for the agent. The agent would then decide on a suitable action to pass to the environment. In this work, we incorporated a virtual adversary from our previous work, which assumes that the attacker has a complete knowledge of the agent, also known as the white box attack, to craft a perturbation action to corrupt the actuator space. The addition of the perturbation to the original action becomes the perturb action, which will be fed into the environment. We ran experiments on lunar lander environment, which the agent can control actuators such as side thrusters and main engine. The goal of the agent is to land safely between two flagpoles without crashing. We have two types of attack, namely L1 and L2 attacks, which is based on our previous work to craft white box attacks. For the sake of time, we are only showing L1 attack results here. This plot shows the results of L1 attack with 4 different settings. The x-axis denotes the reward received by the agent in the environment. The higher the reward, the better. The y-axis denotes the normalized frequency of the obtained rewards. First, we train the nominal agent in the nominal setting, which is without attacks. The performance of this agent is expected where it achieves high rewards frequently. However, when the nominal agent is attacked with small perturbations, it fails to perform as well as before. Then we train a robust agent by introducing some perturbations during training. This shows that the agent still manages to achieve a high reward despite the perturbations. Then we attack the robust agent, which performed really well against those attacks. If you would like to know more on the results, please do stop by and visit my poster during the poster session. If you have any other questions, please feel free to email me. Thank you.
Hi everyone, my name is Qing Li. I'm from CMU. The title of my talk today is Measuring Similarities of Interactive Driving Behaviors Using Matrix Profile. These are my collaborators. One of the challenges in autonomous driving is how to understand and make proper decisions in interactive scenarios. The figure on the right-hand side is showing some examples of pairwise vehicles' interactive behaviors at intersections. The red trajectory is from one car and the blue trajectory is from the other car. For two kinds of interactions, like pair 1 and pair 2, in the left figure, the question is what is the difference between them? The fundamental question is modeling them as two time series and how to compute their similarity or distance. We want to investigate the common subsequences between two time series. The intuition is that two time series are more similar if they have lots of very similar subsequences. Time series 1 is the pair 1 we mentioned before. Time series B is the pair 2. Imagine that we have a matrix. The element Dij in this matrix is distance between the ith subsequence of A and the jth subsequence of B. Matrix profile only stores the minimum values for each column of the matrix. That is to say, it is a vector of distance between each subsequence of A and its nearest neighborhood in B. We further compress this vector to a scalar distance value. We have to mention that a trivial brute force solution is that to directly compute the Euclidean distance using inner product for each pair of subsequences. However, the complexity is very high. Instead, matrix profile uses FFT to do so and significantly reduces the complexity. The dataset we use in this research is from the SPMD program. The first figure in the left is that given a query interaction at the upper left, the subplots B, C, D are the most similar pairs we automatically find from the dataset. The interaction is that one vehicle is waiting at the intersection for a red light, and the other vehicle drives straight forward. The figure in the middle is an example showing the distance we compute. We want to compute the pairwise distance between the first row and the second row trajectories. It can be seen that for the pair D, its most similar pair is A. Pairs E and C are similar, and pairs F and B are similar. For three intersections in the dataset, we evaluate thousands of pairwise interactive trajectories. The average runtime is less than 200 milliseconds in a PC. The contribution of our work is modeling the driving interaction as time series, mining proper, and proposing very efficient algorithm to compute the similarity.
Hello, my name is John Myrn, and today I'm going to be talking to you about exchangeable input representations for reinforcement learning. So to start out with, I want to define what object exchangeability means in the context of a reinforcement learning problem. And to do this, I'm going to take as a running example the aircraft collision avoidance problem, where we want to learn a policy for our own ship labeled 0 to avoid colliding with 3 intruder aircraft labeled 1, 2, and 3 in our diagram. Now, a standard approach for reinforcement learning may be to represent the input to a learned policy as x bar, where the elements of x bar are the relative positions of the aircraft, in this case delta 1, 2, and 3. Now, looking at this problem, we see we could equivalently represent the input as delta 2, 3, 1, or any other permutation of x bar, because any permutation would contain the same information needed to solve the problem. In this case, we say that the relative positions of the aircraft are exchangeable. Now, unfortunately, because x bar and its permutations are mathematically different objects, for a learned policy pi, the output of a policy and the output of a given input is not necessarily equivalent to the output of a policy given a permutation of that input. And this equivalence must instead be learned through the training process, which can decrease the efficiency of reinforcement learning. So the solution to this is to apply a permutation invariant transform, which we'll call G, prior to learning the policy, such that it's the transform of our primitive X bar representation that's used as an input to the policy during learning. Now, an effective transform should not only learn to be permutation invariant, but also more heavily weight more important objects in the problem in the output representation that's learned. So in this case, for our aircraft collision avoidance problem, we'd want our abstracted representation to contain a lot of information about aircraft intruder 1, a little bit less so about aircraft intruder 3, and probably just forget mostly about aircraft intruder 2. So in order to learn that type of transform, we proposed a transformer attention mechanism, which is based on a popular natural language processing attention mechanism. Now, this type of transform has two neural networks in it. One, the filter network, pi filter, which learns the relative importance of all the objects in the primitive representation, and the pi abstraction network, which takes the primitive representations in X bar and embeds them into some higher dimensional space. The invariance is achieved through the use of a summation operator, which is the last operation prior to the output of the final representation. So I don't have time to get into what the experiments were, but we did run some experiments testing the scalability of reinforcement learning both with and without the attention mechanism, and we found that with the attention mechanism, RL was much better able to scale to increasing numbers of exchangeable objects. Thank you. I'm hopefully ready for questions.
Hello everyone, myself is Kushal Chakravarti. We consider solving the linear t-square problem in a server agent architecture. The data matrices A and B are distributed row-wise among a number of agents. Each agent holds only its own data, AI and VI, and does not share that with anyone. The task of the agents is to minimize the aggregate cost and obtain a common global minima. For now, we are assuming that the matrix A is full rank. Among the existing methods that can be applied to solve this problem, the gradient descent method is the simplest one. Among the variations of the gradient descent method, the heavy ball method is shown to be fastest. Recently, a projection-based method has been proposed, and it has been experimentally shown that this method works faster than the other methods. However, this method is applicable only if the system of equations Ax equal to B has a solution. Also, this method involves additional computational cost. The rate of convergence of all these algorithms is directly or indirectly influenced by the condition number of the optimization problem. So we are proposing a novel technique called iterative preconditioning, which helps in reducing the effect of condition number on the rate of convergence. Our method is guaranteed to converge faster than the traditional gradient descent method with no additional cost. From the experiments, we have observed that the proposed method also converges faster than the other methods. In addition, the proposed preconditioning scheme can also be applied to the stochastic gradient descent algorithm, which is a standard technique for linear regression problem on a large datasets. For the details of our algorithm and the theoretical convergence guarantee, you can refer to our paper. Let me share some of the experimental results that we have. We considered 4 different benchmark datasets, 3 of which have very large condition number, as you can see from the second column of the table. In each of these cases, we compute the number of iterations an algorithm would take in order to get a satisfactory solution. So from the green colored cells in the table, you can see that the proposed algorithm requires given number of iterations compared to the other algorithms in all 4 cases. And from the blue colored cells, you can see that the rate of convergence of our algorithm is improved upon the other existing algorithms. In our ongoing work, we have obtained theoretical basis for the improved convergence of our algorithm over this existing state-of-the-art distributed algorithm.
Hi everyone. Thank you for attending the presentation of our paper named Towards Scalable Kuma-Operated Learning, Convergence-Rich and Distributed Learning Algorithm. This is a joint work with Guohui Ding Lijun Chen from UC Boulder, and Enoch Yang from UCSB. The Kuban learning problem attracts a lot of research attention recently and has already been applied to a lot of areas, such as robotic control, nonlinear system identification, and image processing, to just name a few. The key of this problem is the Kuban operator theory. It tells us that for nonlinear dynamic system, we can find a function space so that if we project the state space into that function space, the dynamic will become linear. Based on this theory, the Kuban learning contains two simultaneous tasks: learning the function space, and in the middle, learning the linear mapping. In our paper, we focus on the current issue incurred by the training process, the convergence, and the distributed training. Since a lot of applications only have the local operations, which requires the distributed training. We thus propose an alternative optimization algorithm to handle this issue based on the gradient descent. In our analysis, the key assumption is the basis function is bounded, has a bounded gradient and Hessian. Please note that this holds for several popular activation functions adopted by neural network, such as logistic function, hyperbolic tangent function, inverse hyperbolic tangent function, etc. Our main results show that this alternating optimization algorithm will converge to one critical point with sublinear rate. We also proved that it's easy to extend this algorithm to distributed training if the basis function is decomposable. Our experiments show that alternating optimization together with distributed training achieve good prediction performance with simple and shallow neural network. For example, we only use neural network contains 1 or 3 layers. For more details, please refer to our poster session later.
I'm Giacomo Baggio from University of Padova, and the work I'm going to present is about the data-driven computation of minimum energy controls. It's a joint work with Fabio Pasqualetti from University of California, Riverside. So let's consider a discrete time dynamical system with state X and input U. We are interested in computing the t-steps input sequence, driving the system from a given initial state to a target one with the least possible effort. This is the minimum energy control problem that has many applications across different domains, especially in the control of biological and technological networks. If the system is linear and we know the model of the system, then there is a well-known closed form expression for the computation of minimum energy controls, which is given in terms of the controllability Gramian of the system. Assume now that we don't know the model of the system, but we have a set of data generated through control experiments. In each experiment, we apply a t-steps input sequence to our system, and we measure the corresponding final state. In this setting, it has been shown that if the input experiments are sufficiently exciting, then it is possible to compute the minimum energy input directly from the available data. The aim of this work is to extend the applicability of this result to more general settings. In particular, we consider more general datasets. That is, we allow data to be recorded from experiments of possibly different lengths. In this case, if a rank condition on the data matrix is satisfied, then it is still possible to reconstruct the minimum energy input directly from the available data. In addition, this is possible for any control horizon that can be written as sum of lengths of the control experiments. Then we consider the case of noisy data. In particular, we consider data corrupted by IID noise with known second-order statistics. In this case, we establish asymptotically correct data-driven expressions of minimum energy controls. This means that these expressions tend to the optimal ones as the number of data tends to infinity. That's all, thank you, and please join the interactive session for further details.
Hi, my name is Elvis. I'm from the University of Notre Dame, and I'm going to talk about learning and optimization with Bayesian hybrid models. In this work, we ask the question, how do you make decisions under uncertainty with limited data? We consider two kinds of uncertainty: aleatoric uncertainty, which arises out of random phenomena, such as experimental variability, and can be described using probability distributions, as well as epistemic uncertainty, which arises due to model inadequacy, such as simplifying assumptions or approximations, leading to a systematic bias in the model. These are difficult to describe, but Kennedy and O'Hagan provided a fully Bayesian framework to simultaneously calibrate aleatoric and epistemic uncertainty. These hybrid models have a glass box component, which is a simplified physics model described using parameters theta, a Gaussian process discrepancy model, which accounts for model inadequacy and is described using hyperparameters phi, as well as normally distributed random noise. We use the hybrid model in a Bayesian decision-making workflow in a simple computer experiment to try and hit a target 100 meters away using a cannonball without accounting for air resistance. The data for this experiment are impact locations recorded at 6 combinations of firing angle and muzzle velocity, simulated using a full physics model. We use this data to calibrate a hybrid model using Bayes' rule, from which the posterior distribution is used as the uncertainty set in a stochastic program. The objective of this single-stage stochastic program is to find the angle and velocity, which minimizes the distance between the impact location of the cannonball and the target location. We see here that the pink dot shows the prediction from the Bayesian workflow, and it nearly coincides with the prediction from the full physics simulation of a direct hit. Moreover, the shape of the contours of the hybrid model indicate that the hybrid model retains physical information from the glass box model, while its data-driven discrepancy model augments its predictive ability, resulting in almost a direct hit. In conclusion, we see that Bayesian hybrid models outperform simple physics and black box models when limited data is available, and thereby facilitate the extension of stochastic control to consider epistemic uncertainty. We are working on improving the scalability of the Bayesian hybrid model decision-making workflow by the optimum selection of training data, and also trying alternate calibration procedures. Thank you.
Hello everyone, thanks for coming. Today I'm going to talk about our recent work on optimal control-inspired Q-learning for switch linear systems. Generally speaking, Q-learning can be viewed as a data-driven approach for solving optimal control problems. For simple problems like LQR, knowledge about analytical properties of the optimal solution can help developing effective and efficient Q-learning algorithms. However, how to incorporate the optimal control insights into problems with hybrid systems remains open. In this work, we consider the optimal control of switch linear systems, which is trying to find the optimal continuous input law and discrete switching law to jointly minimize an infinite horizon quadratic cost. One of the key results from classical optimal control is that the value function to the above problem can be approximated arbitrarily well by a pointwise minimum of finitely many quadratic functions as shown below. Inspired by this analytical result, we propose to directly use PMQ function class to parameterize the Q function instead of using neural networks. Parameters used in this approximator are the matrices defining the PMQ structure, which need to be updated based on information from training data. Due to the underlying PMQ structure of the optimal value function, it can be shown that the training data satisfies the following geometric property. By exploiting the PMQ structure of the value function and the associated geometric property of the training data, a geometric identification algorithm is proposed for updating the matrix parameters in the Q function approximator. Details can be found in the paper. We first test our geometric identification algorithm with synthetic data, distribution of the data samples and level sets of the underlying PMQ function are plotted on the left, and error distributions with different number of approximation matrices are shown on the right. The overall algorithm is tested on an 8-dimensional problem with 2 subsystems. Convergence of the value function at several sampled states are shown. To sum up, the high-level objective of this work is trying to bring insights from classical optimal control into developments of Q-learning algorithms. We focus on switch linear systems particularly in this work, and in the future, we aim to extend this idea to more complicated hybrid systems. That's all. Thanks.
Okay, everyone, thank you for attending this RI session. And I want to remind everyone to visit the interactive session starting now until 11:45. And then also please vote for the People's Choice Award for this RI for this particular session, and then look at the information on the Hugo Shuckleworth. Thank you very much and have a good time at ACC.